Alright, hello and welcome to the review lecture. So you do not have to watch this, but I do encourage you to at least skim through it at 5 times the speed, just to make sure you know all of this stuff. Because all of these topics that I'm going to go over are stuff from CSCI 40 that I need you to have ingrained in your minds, okay? We're going to need all of this information, all of this knowledge, essentially on the first day of class, okay? So thank you for watching, and let's get right on into it. So the first thing that I want to talk about is const. Const is like a specifier that you can put at the front of a variable name. So you can say something like const int. Const modifies the int type, and you can say x equals 42. Okay, and then for the rest of the program on down the line, this x variable, it's an int, cannot be changed. Okay, so hopefully it's all coming back to you. Const is for when you have a variable and you do not want it to change. Okay, so let me give you an example of that. In code, I have a nice fresh CSCI 41 folder for us to work with, and I'm going to make a directory called, I guess, CSCI 40 review. And let's go on into that and get started. So I'm going to edit a file. I guess let's just call it const.cpp. Okay, so what is going to happen is everything that I said should make sense, right? Const int x equals 42. Now it's a constant. It cannot be changed. If I say x++, this won't even compile. Okay, you can see that I'm getting an error. It's like, cannot assign to variable x with const qualified type. That's beautiful, because this is supposed to be a constant. We should not be allowed to do this, okay? That's exactly what we want to happen. Okay, that's lovely. And so that is essentially constant in a nutshell. It just modifies a type. You can say double, you can say bool, whatever you want to not change, you put there. Okay, and usually we don't make a whole lot of const variables. Maybe you make a variable for pi or something, but a lot of the time we make const parameters to functions. Okay, and that is to keep ourselves from shooting ourselves in the foot. Okay, so let's make a simple function I don't know, add1, that returns x+1 or something. And what we like to do a lot of the time is to say const in x when we're not going to change x. Okay, it's common practice to make parameters const when we know we don't need to change them. We're not going to be touching x in this function. It would be a mistake to touch x in this function. So we are going to make sure that everybody knows about it being const. So anybody who sees your code knows that x is not going to change. And then also anyone who tries to edit your code, this would be an incorrect add1 function, right? It would add 2 if I were allowed to add this line 7. Now I'm no longer allowed to add it. Okay, that's beautiful. The const is protecting me from making mistakes like this, and that's why we like it. Isn't that beautiful? And then the final piece of the puzzle is you don't have to have a const variable that you pass to the add1 function. Okay, essentially any variable can be converted up to a constant when you pass it. So that's quite nice. That's essentially in code the same as doing something like, I don't know, having an int y and then saying const int z equals y. That's essentially what's going to happen when I do this, because I can say add1 of y or something, and I can print it out if I want, but there's no use right now. This y variable, it's not a const. It's just 43. But when it gets it, when I put it into x in this function, for that entire lifetime of the function, that x holding 43 cannot change. Okay, so you can convert up, we say, to a const. Yeah, so that is the idea with constants, and we love to put them in our function parameters. Okay, yeah, let me show you me running this program. It doesn't do anything. Maybe we'll make it printed out right down here. Cout that and a new line. So in theory it should print 44. I'm going to compile and run this program, and depending on your CSCI 40 class, you may not have touched a compiler. So let me show you what's about to happen, how we get to the nitty gritty. Here I am on the terminal. I'm going to teach you this on the first day of class if you don't know it. Let me get into the CSCI 40 review folder. Inside of that, there should be a const.cpp file. Beautiful. I'm going to compile and run this program. Okay? Compile and run it. So what we do to compile is we use the G++ compiler. It stands for the GNU C++ compiler, and we like to use the latest version that's supported, which is the C++ 17 version of the language. And so every program that we compile is essentially going to start with this G++ standard equals C++ 17. Then you give the name of the program that you want to compile. Potentially you have many programs, many files that you're giving to make one big thing, like maybe you're putting a bunch of functions in different files. And then you give a -o parameter if you want to have a special name for your program. So the output of the compiler is going to end up in this out file, if we say it like that. So that was a lot. If you've never seen that before, don't worry. You're going to become pros at it. So this is essentially what I need to do. I need to say G++ standard equals C++ 17 const.cpp, and then if I don't give anything extra, it's going to compile it into a file called a.out, which is kind of useless. It will work, like I can run it, 44, cool, but a.out is a silly name. So that's why we use the -o parameter, and we'll give it a name const. So now I have two files in this folder, const.cpp and const, which is the program that I can run. Okay? I can say /const on the terminal to run it. It does the thing, and I'm back at my terminal prompt. Okay? So that might have been a lot. Don't worry, you're going to see this a whole lot more, but this is where you need to go if you haven't been there before. Okay? So const. Beautiful. Now let's get into references. We love references, right? So a reference, it's an alias for another variable. If I say int x equals 42, I can make a reference to x. Call it y maybe. Int reference y. The ampersand and a type means reference. And I say equals x. And essentially what's going on under the hood is I just made this, on this line, I made the variable x, right? It holds 42. And then I come along and I say, oh, y is going to be a reference. Y is a reference to x. We kind of read it in a weird way like that. And what's happening is I essentially have two names for the same variable. I can say x++, and it's 43. I can say y++, and it's 44. Saying x or saying y has no difference. They are the same little box in memory. Okay? That's beautiful. And references are quite nice because they let you save memory because things don't get copied. You're reusing a box, okay? So we like to have reference parameters a lot for large types. Like if you have a big fat vector, I don't know, you're doing something with a vector maybe. And then you have your implementation, blah, blah, blah. A lot of the time what we like to do is instead of passing along the vector v, which means it gets copied, we like to say reference. We put a little reference right here, an ampersand, to make sure that this vector v is being reused. Okay, so when you're in your main function, you make it. It's not going to be copied when you call foo. Okay, so that's the idea with references. And a lot of the time, we also like to say const as well in our parameters. Const reference parameters, because not only do I not want to copy this vector over when I use it inside of a function from somewhere else, I also don't want to be allowed to touch it. So this becomes the full parameter type. It's a constant vector of int reference, call it v. Okay, so I'm not allowed to touch v inside of this, and v is not getting copied from somewhere else, like in main when we call it. Okay? So that is references and const references in a nutshell. Maybe I should like edit our file to do something silly like, I don't know, const reference to an int, which is very useless because ints are very small in our computers. It's just as much work to send a reference than an original int. But just let's pretend right now nothing should actually change. Okay, so x is not being copied. It's sharing the same box as y, right? Sharing the same box as y when we pass it along. And also it is a reference. Okay, it's const and we're not allowed to touch it. Okay, so again, nothing changes. Beautiful. Const references. Essentially, whenever you write a function and you have a parameter, what I want you to have in your mind is this pattern. Always make it a const reference when it's a non-basic type, unless the compiler complains. You always want it to be a const, and you almost always want it to be a reference. Okay, so those are references. Let's talk about pointers now. So a pointer is like references on steroids, right? We can touch the individual memory now in a way that we hadn't been able to do before. So pointer, it's just a variable, but the variable holds an address. That is the key. That is all you need to know to work with pointers, right? So when I say int x, what I do, let's give it a value, why not? What's happening in memory is, like, your computer doesn't know anything about x. It makes a box in memory, yes, but it has no clue what x means. X is just for you, the programmer. What it sees is an address. It's like, okay, my variable x, it lives at the address 100 maybe, inside of my memory. Okay? So a pointer is how we can talk about these things, these addresses, these essentially the names of these boxes in memory. So it holds 42, and what I'd like to be able to do is make an int pointer, okay? Int pointer p maybe, that is holding the address of x, okay? So that's what this is doing. We make an int pointer p, and it holds the address of x. And so p, maybe it lives at address 108 or something. Take a minute, pause the video, what is going to go in this box when I say this? What does this all mean, right? Keep this in mind. A pointer is a variable that holds an address of another variable, usually. What does this mean? What is going to go in here? Well, it's going to be the address of x. It's 100, right? And so suddenly we have a way to talk about these boxes. And in a diagram form, bam, this is what's going on. Okay? P is pointing to x, and I can touch x. So let me make a program, and then I'll draw a stack diagram as well. So let's make a pointers.cpp file, and I'll make my int x and my int star p equals, let's see, you know what? To get the most out of a pointer diagram, how about I make a function again? Int add 1. This time we'll take a int pointer, and we're going to return one more int later, okay? So essentially what I want to be able to do is follow this pointer p to this int, add 1 to it, and return back 43, okay? So using a box with 100 in it, how do I get 43? How do I follow it and get 43, okay? So just remembering how to use pointers to get the value out, to follow the pointer and get to the int, we say star p. Yeah? So we dereference p, we say. And if we return that, that follows p to the int that it's pointing to, and add 1. We should also add 1. So I should say +1 right there. Okay? And so to call this function now, what's happening is we can say, add 1, and then we give the address of an integer variable. Well, I got an integer variable right here. Let's give the address of x. Okay? And so this should print out 43 if I add couts everywhere. And so let's do this. Let's make sure it's working, and then I'll draw a stack diagram. All right, so now it's compiled into this file called pointers. Okay? Bam, I get 43. Beautiful. And so now let me show you how this is working. So, when our program gets run initially, we have main. Main is called for us like by the terminal, we can say. And main has a variable called x, which let's pretend lives at address 100, it holds 42. And then, when I call this function add 1, I am passing along, in the call, the address of x. Okay, so I'm passing along that 100 in my example. Okay, so I have add 1, and then it takes a p variable, which has its own address, but we don't really care about it, but it holds the address of x, so it's pointing to x just like that, okay? And this is how it gets to 43. It follows p with the star p, gets to this box here, and now it can touch its memory value, and then it adds 1 to that result, and that's how we get back to 43. Okay, so this is how we can, this is one way to pass along information across function boundaries. Because x is a local variable, it doesn't exist up here. I can't say x inside of add1, because x doesn't exist. Okay, there is no x variable up here. But p is how I can get to this one. Okay, hopefully it's all coming back to us. Please yell at me on Discord or anything, anywhere, if you have any questions about this stuff. Come to office hours, definitely. So yeah, that's pointers. Let's keep on trucking. So I have shown you now lots of functions, right? Functions with const, functions with references, functions with pointers. There is a nice trifecta, I guess, of different ways to pass values to functions. And we have call by value, call by reference, and either we say call by pointer or call by address. Depends on how you're feeling on the particular day that you're saying that word. So let's make the quintessential swap function. Okay, it's going to swap the value of two variables. We know that that is not a trivial task, though it's somewhat trivial now to us. Maybe we have x being 42 and y being 43, and what we would like to do is have them swap their values. And so at the end of the day, x is 43 and y is 42, and we hopefully remember that we have to make a temp variable, because the second you assign one to the other, now you've lost the other one, right? So yeah, let's make a swap function, and I'm going to show you the 3 different ways that you could do it, and let me leave myself room down here so I can draw 3 different stack diagrams. So let's like bring that there. No, we lost the 4, sorry. Up you go. Okay, so I'm going to make 3 different kinds of functions. One call by value, where things get copied. Copies get made there. Call by reference, which is one way to share variables across function boundaries. And then the one I just showed you, which is call by pointer, or call by address, and that allows you to share variables across function boundaries indirectly through pointers. Okay, so let's go. Let's make a new file called, I guess, callby.cvp. Why not? Okay, so I'm going to have int x equals 42 and y equals 43. So 2 int variables. And let's call swap value reference pointer. Okay, swap value xy, swap reference xy, and swap pointer xy. And so let me declare all of these. So void swap value. This is without any modifications, like, I don't know, int a, int b, no ampersands, no stars. This is just by value, ints by themselves. So that's one function. And then I'll have 2 more. Swap value, swap reference, which is going to take, I think you guessed it, a reference. So it's going to take 2 references now. And then the last one is going to be swap pointer, and let's make these pointer variables. And so I really encourage you to like pause the video and try and fill these in. Like, we want to swap things in all these different ways. How do we do it? Okay, and actually I called this one incorrectly, because if I'm going to call with pointers, I can't just pass ints. Those are not pointers to ints. There's a difference. So I have to pass along the values of the addresses, okay? I have to pass on the addresses of x and y there, okay? So essentially, here is how I'm setting this up. In main, like, I have x and y, yes. This will be 42, 43. Now let me do this twice more to show you the 3 different functions that I'm about to call from main. Main xy 42, 43. And then for reasons, I'm going to make in this one x 43 and y 42. Just for fun. Okay, and so this one is swap value, this one will be swap reference, this one will be swap pointer. Swap pointer, and it has a and b variables, right? So a and b, a and b, and this one also has a and b. So let's like draw how this is all getting called here. Right now they're just empty functions. Don't worry, we'll get to that in a second. Okay, so, oops, did I accidentally move that around? Sorry. Let's see how I can get rid of that. Oh, there we go. Okay, so let's pretend we're calling swap value with x and y. What's going to happen? Like, what are the values of a and b? Well, they're going to be 42 and 43, right? So 42 and 43. And then let's swap them, right? We remember how to swap, right? We go to up into here, we say int temp equals one of them, and then a equals b, b equals a. The pattern is the last thing at the end of the first line is the first thing at the start of the second line. They mirror each other like that. Okay, that's how you correctly swap something. And I think you remember that this one doesn't work because, oh no, like temp equals a, 42, sure, b equals a equals b, 43, b equals temp, 42, cool. Did x and y get changed at all? No, they were just copies. This is what happens when you pass by value. When you call by value, you're just copying things. Okay, so it's kind of useless for a function called swap because it's swapping a and b, but we kind of wanted it to swap x and y. So if I print out the values here, like nothing happens, right? We see still we're going to see 42 and 43. Okay, so okay, let's move on to swap reference. When I say x, y, that means a is a reference to x and b is a reference to y. How does that work in the diagram? Well, remember with references, like there's no new box. Like let's just pretend that everything in swap ref is green. Now suddenly here's a, here's b. Okay, I say a and I get the original x. I say b, I get the original y. That's how references will work across function boundaries like this. And notice I can't say const. I can't say const because I want to change these. I want to swap them. So again, I can actually have this same exact code, but this time a and b are actually touching the x and the y because of the reference. Okay, so temp lives up here, yes. Temp gets 42, then a is set to b, so 43 goes here, and then b is set to temp, so 42. And so we correctly swap things, and we'll see 43 and 42 after swap ref returns, and we go back into main, right? So that's beautiful. They let you touch the original memory, swap reference and swap pointer. So swap pointer is a bit more involved, but we can make it work. Okay, this one will also work because we can share that memory. We just have to follow a and follow b. Okay, so instead of a, we say star a. Instead of b, we say star b. Star. Star. Okay, and so now we're just following these pointers and getting to the memory that they're pointing to and changing them. Temp is still in it. It just holds in it still. So here's what's going to happen when we call this one. So we set a and b to the addresses of x and y. Let's just pretend that they're like 100 and 104 to make it easy on us. So a holds 100, b holds 104. We don't want to swap these. We want to follow those pointers because they look like this, right? We want to follow them and swap the values that they're pointing to. So we say star a. Now we put that in our temp variable. Temp equals star a. That's going to get the 43 out. Okay, sorry, this is so small. And then we say, okay, a star a now equals star b. So we're setting the 43 over to the 42. We're like bringing the y into there. Okay, and then we say star b, sorry, to talk about this memory right here. Star b equals temp. Okay, and so that makes it 43. And this is a 2. Okay, and so that correctly swaps them back to their original form. Okay, so that is all the different call bys in a nutshell. This one won't work, and these two will work. Okay, so let's go and compile these. So we say g++, and we get the name of the file, call by, and I usually just like to make the program called the same name as the file, so call by, and so there it is, /call by. Yay, so the first time it doesn't change, because they start out 42, 43. The second time, oh shoot, sorry, I didn't say temp. I'm so sorry. I'm sure you're yelling at me through the screen. That should do it. But that's why we test these things. So the first time it doesn't work, second time it does, and then the third time it also does. It swaps them back to their original form. Okay, so that's all the different ways you can pass parameters to a function, and sometimes it's good to copy things. A lot of the time you don't want to though. Okay, so that is the idea with all of those. Following up on pointers, let's talk about the heap now. So the heap is a special place. Like inside of all these, like inside of main, we can have our x's. We can have all our variables. But this is local. Like maybe if I had a foo function and it made a y variable, and I set this to some important value, the second foo returns, like this information goes away, all of its local variables are deleted, right? We don't like that. We don't like that one bit. So how do we fix it? What can we do? We can put memory into a separate place. Like these are local variables, local variable, local variable. We can make essentially global variables in a place called the heap, because this is the stack. It's where local variables live. And the heap is a special place where magical dynamic memory lives. Okay, so I can make a box on the heap. Oh, that's interesting how it's doing that. If I turn off the automatic saving, that'll fix this. So, yeah. I could have sworn I just enabled the eraser. Let me erase, please. Well, I can always redraw it, I guess. Oh? I can't redraw that. Well, sorry about the technical difficulties, but I think you're getting the idea. Oh my. So like behind everything somehow? That's the weirdest thing I've ever seen. But okay, we'll just keep it circled, who cares? What happens is this is shiny new memory and it doesn't go away, okay? It lives on the heap forever. That is the beauty of it. Okay, and just to keep myself sane, I think I will restart PowerPoint because this is a weird little bug that I've encountered. So I'll be right back. Okay, let's try again. And apparently I just forgot about everything I drew over here, so heap. This is a shiny new variable, and we can make it, like we can make a variable z that points to this place on the heap, and even when z goes away, we still have this box. That is the beauty of heap stuff. Things that you, memory that you want to create on the fly, and you want it to live for as long as it needs to live, as long as you want it to live. Okay? So, I guess let's just do a simple example of this. Heap.cpp, let's edit a file called that. And let's say, I don't know, int star I or something. To make something on the heap, we say new, and then the name of the type. Okay, so new int, what it does is it returns back a pointer to a place on the heap. So this code, new int, when we say it like that, returns back a pointer to a new int on the heap. Okay, it's fresh, it's new, and we can set it. We can say star I equals 42. We can print it out. That's fine. And then once we're done with it, usually you do this across a bunch of functions, but I'm just being lazy. Once we're done with something on the heap, we delete it. And then we should never use it again. Okay, so we say delete I, and this goes into the memory in the heap at I and gets rid of the thing. Okay, so essentially what I did was I made a variable called I, and it pointed to this place on the heap, and I set it to 42. We can print it out, and then I said delete I, which doesn't delete a local variable. You can't delete a local variable. It goes to the heap and deletes this variable here. Okay, that's what delete does. It goes and deletes dynamically allocated boxes, dynamically allocated memory for you. Okay, so that is the heap in a nutshell. And a lot of the time we make more than just an int, right? We like to usually a lot of the time we make arrays on the heap, and in this class we'll talk about how to make a bunch of different data structures that make a whole lot of use of the heap and of dynamic memory. Okay, so arrays, if you declare them in C++, like int r or something, equals 1, 2, 3, secretly in memory, this is what it looks like. R, like I like to draw them like this, but this is technically not correct. 1, 2, 3. Really, what's going on under the hood is R is a pointer. Usually you say R1 or something like that. But when you say R by itself, when you say just the name of the variable that represents this array, a pointer. It's just a pointer. It's weird. So really what's going on is R is a pointer to a piece of contiguous memory, still local variables and everything. 1, 2, 3. It's a pointer to the start of this memory. So like this is address 100. Ints are 4 bytes long, so this will be address 104. It's guaranteed to be. This is address 108. It's guaranteed to be. So this is really what the array looks like. You say R by itself, you get the 100. Weird, huh? So an array, it's just a bunch of contiguous memory like this, and you can make arrays on the heap because sometimes you don't know how many elements you need at the beginning. Okay, so this is just a long-winded way of me saying that int star heap r makes sense, because you can just as easily assign an array into an int pointer as you can into an int r with some brackets. Okay, so to make an array on the heap, you can say new int, and then you give the size of what you want, and a lot of the time this is in a variable. Okay, it's dynamic memory, it doesn't matter. You don't have to upfront say, I want this exact many things. It can change as the program changes, as the program runs and gets a new input maybe. So let me just show you that quickly. You can say int star r equals new int of 42. And this doesn't have to be a hard-coded number. You can get it from the user, you can see in a variable or something, and use that. And then you can set these things. Like this syntax still makes sense even though it's declared as an int star. Like r1 equals 42, r0 equals 43. Okay? You can touch it just like this. Don't go beyond index 41, of course. So that is an array dynamically made on the heap, and you can get rid of it. You can say delete, this time with brackets. Okay? So if you want to delete an array on the heap, you got to tell it like this pointer that I'm giving you, because it is just a pointer again, it's a pointer to something bigger than just one int. Okay? That's all. So that is arrays on the heap. Hopefully it's all coming back to you. And yeah, 2 more slides, then we're out of here. So next we have vectors. We love vectors, right? They are the easy form of arrays. Like you don't have to worry about size. They like things get made for you. It resizes itself. Secretly, it's using the heap. It's using dynamically allocated memory, dynamically allocated arrays, and you'll eventually implement that in this class. Isn't that fun? So a vector, it's just like an array, but you can add to it as much as you want. So you say, I don't know, dun dun dun. You got to include vector, of course. And then you can make a vector of things. Vector int v. You can give it initial values, you don't have to. And then you can start adding to it. You got push back, right? Isn't that cool? And you can iterate through it. v.size exists. And you can say cout v at I. Technically, you can also use v of I like that, but this one's better because it throws an exception when you go too far. We prefer that in this class. So yeah, that's like the normal way, the early 2000s and before way of iterating through a vector. You can also iterate through a vector by using a range-based for loop, we say. Oops, I want to keep that actually, but I want to copy it. You can say for int I, and the colon means in. For every int, call it I, inside of v, print out the I, please. And so this just goes inside of it. It's called a range-based for loop, if you haven't seen it before. It's equivalent to the one above. It's just going through the vector in order. Okay, so here's my main function. Let's go ahead and compile and run this. Oh, I never saved it. That's why it was unhappy. Are you happy now? Yeah. And so what this is going to do, it's going to iterate through the thing twice. Okay, same stuff, no difference. And that is vectors in a nutshell. Hopefully those are all coming back to you. You can pass them around. It's quite fun. If you're ever wondering about like what is inside of a vector, you just search Google and c++.com comes up. And you can see all the cool stuff that you can do with a vector, examples of its constructor, how to make vectors in cool different ways, like a fill vector is nice because it can make a bunch of things with the same value. This makes this initializes this vector with 4 ints with value 100. It's got like 4 100s in them. You can copy them, things like that. So that is a vector, and so we just used size, which gets the size, tells us about what it is, its return type, and all that. So do use this website. We're going to love this website in this class. We're going to use it so many times. We used at. I showed you this operator. What else? What else? Push back. There's also a pop back. It shows you a nice little way of using it. It's a wonderful website. So yeah, vector, it's just like an array. You can add to it as much as you want. Secretly, it's using dynamic memory. So that's a reason to care about this stuff if it was seeming a little too fuzzy and weird and up in the air. Okay, so we're going to learn to make our own vectors in this class. So look forward to that. And then finally, let's talk about exceptions, because a lot of the time we can do silly things and we want to make sure that we can get ourselves out of any problems caused by those silly things. So like let's say I try to cout v at. So there are 6 things in this vector right now. Index 0, 1, 2, 3, 4, and 5. So what will happen if I try to do this? Bad things, right? Whee! So I get, after it does all its cool stuff, it throws an exception. This is called an exception. It stops the program because I'm not handling that exception. It's particularly called an out of range exception. It tells me what went wrong. Oh, 6 was bigger than the size of the vector. The size was 6, so you should have only gone up to 5. So so it throws an exception, and it also stops the program if we don't handle it, let's say. Handle the exception, that's the key term here. How does one handle an exception? Well, I have a nice contrived example for you. Let's talk about throwing exceptions and catching them, and try and catch and all that good stuff. My running example will be somebody tries to order pineapple on a pizza, and obviously that's an error. So we're going to throw an exception and alert the user that their program is trying to be, that it's being used incorrectly. Okay? So let's make a new file, exceptions.cbp. And so, let's see what we want to do here. So let's make like void up here, void order pizza. Let's make a function. And we'll have like a string kind for the pizza. Okay? And so if I want to use strings, I gotta include string. And I can say stuff like, okay, if kind is unequal to pineapple, then like I'll see out the pizza or something. Here is your kind pizza. New line. Else, the user tried to order a pineapple pizza, or pizza with pineapple on it. We don't like that. We should throw an exception here, okay? We want to alert the user, like whoever's calling this function, that an exceptional occurrence happened, okay? That is the idea. So we can say, what's the best way to do this? If we want to raise an exception to say, hey, somebody else deal with this problem, we throw it, okay? And you can throw anything inside of C++. You can throw any type, okay? You can throw an int if you wanted to. Usually you throw an exception type, but hey, let's just do it the weird way. So let's do order pizza, pepperoni. I think there's 2 P's, right? So there's 1. That one's not going to be an exception, right? Hopefully. Let's try it. Dun dun dun. Here's your pepperoni pizza. Awesome. Now let's try to order a pineapple pizza. Really, I should have like passed a vector with a bunch of different toppings, but you get the idea, right? And bam, after the pepperoni, we have an exception that gets thrown. Terminate called because we didn't catch it. Throwing an instance of int. And so what's happening here is this is going to throw an exception. If we don't want it to stop the program, we need to catch it. So do you see the metaphor that's going along? Like, we have a problem, we throw that problem to somebody, and hopefully along the line somebody catches it. Okay, so here's how you do it. You say try. This is called a try catch block. So inside of the try, you put anything that might go wrong. You put code that might throw an exception. Okay, and then you say catch. Let's have it throw a string this time, because why not? And this is secretly not a string. You have to wrap it in the constructor if you're gonna return it like that. So that throws a string, and so we want to put this inside the try, because it will throw an exception. We know it will. But technically, we should put anything that might throw an exception in there too, okay? And then, if an exception occurs, you're going to be teleported straight to the catch block, anywhere inside this code. Like maybe it calls a bunch of inner functions. It doesn't matter. It's going to go to the closest catch block that can deal with the type of thing that got thrown. I know that is a very long sentence, but let me just show you this in action, and hopefully it'll make sense. So you say catch, kind of like a function. You catch the thing that's being thrown, and usually you catch it by reference. So catch a string s. So in here, in the catch block, well, usually you catch by reference, and inside the catch block you handle this exception that just got thrown. We only get here, we are only ever here, if an exception gets thrown. So we need to handle it now, okay? So we have to handle it. So see out, I don't know, we'll say like, uh-oh, or try again, and be like, we got this. Okay, and so this will not stop the program. It'll just be like, okay, an exception got thrown. We knew how to handle it. We knew how to handle a string if a string got thrown. So we're not going to stop the program. Okay, that's the beauty of it. Bam, bam. Awesome. So the pepperoni works out, and then we jump straight to the catch block and handle the exception. Notice, an important thing to notice is the second an exception gets thrown, we jump out. So we will never execute this code right now. Okay, we're never going to get to pepperoni because it goes straight here and then it continues with the rest of the code, which is the rest of the program in our case. So just keep that in mind if you ever have a try-catch block and you want to do multiple things. The second an exception occurs, you're going to be jumped out. Okay, that is potentially an issue. And usually, instead of throwing strings, we like to throw exception things. So where is it? Normally we include standard except, and we throw kinds of exceptions. Usually it's like a runtime error. That's the one I like to throw. So a runtime error, it has, let's see here. Bam. What do I want here? Are you going to show me anything useful? Yeah, so this is essentially what we want to see right here. So a runtime error, it takes a string or a C string, and that tells you like what went wrong. Okay, so normally that's what you do. So instead of this one, we'll do throw a runtime error, and then you give like a description inside. So normally instead of a string, you would throw a runtime error because it has a string inside anyway. Okay. Dun dun dun. So there's that. And now, instead of catching a string, catch multiple things. Like, okay, if a string gets thrown, I'll do this. Otherwise, let's do it here, I guess. Otherwise, if a runtime error gets thrown, then be like, uh-oh, we got a runtime error. And here we can say we got a string. And instead of S, to get the string out of the exception, when you have a runtime error, that is, you say what, okay? That's a funny little method that exists. It returns back the string of what went wrong. You just say, oh, exception happened? Well, what happened? You say r.what. Isn't that cute? Isn't that cute? Okay, so, yeah, I think that's all. So run it. And so this time we're throwing a runtime exception, or runtime error exception up here, and we're catching it, we're handling it, the rest of the program happens, and we're done. Okay? So that's how you like stop things when things go wrong. Alright, so that is exceptions in a nutshell. And yeah, remember to try and then catch. Remember that you're plopped out of the try whenever the first exception happens. Exceptions are thrown and you catch them. Yeah, it's all about recovering from problems. So that is everything that I wanted to review. On the first day of class, I'm going to go over classes and structs. So you can wait until then to have a review on those, but just make sure you're up to date and not too fuzzy with any of these topics that I just went over. Okay, so that is the review. Pat yourself on the back for making it through, and I will see you on the first day of class. So, see you then.